Hey, welcome back. This chapter is about a spontaneous potential, also known in Wireline logging as SP. After completing this section, you will learn to understand the origins of spontaneous potential, identify SP key applications, determine possible sources of error on SP readings, describe the baseline responses in shale, also to analyze SP responses to the ratio of resistivity of mud filtrate and formation water resistivity. And finally, you will classify invasion profiles using SP logs. Let's begin. The spontaneous potential SP tool is designed to measure a natural or spontaneous current flow between the borehole formation. What we measure here is a really small voltage between an electrode in the surface called fish and another electrode in the tool which is inside the borehole. SP deflections arise from currents flowing in the mud-filled borehole and formation, driven by two main types of processes, electrochemical and electrocinetic. Let's define these processes and their subcategories. Electrochemical processes involve ionic imbalances between fluids. When two fluids with different ionic concentrations are in contact, ions migrate to the fluid with lower concentration, creating a current flow. There are two specific types of electrochemical processes. First, membrane potential. This occurs in formations with shale. Clay minerals with negative charges repel negative ions and allow positive ions to migrate, creating an electromotive force called the membrane potential. This potential causes current flow across the formation boundary, affecting the SP measurement. Secondly, we have liquid junction potential. This happens when mud filtrate with different salinity invades the formation. Ions migrate at the boundary between mud filtrate and formation water, creating a liquid junction potential. This also generates current flow and affects the SP measurements. Finally, electrocinetic processes involve fluid movement at the borehole formation interface. As fluids move through more porous media, like mud cake, they transport ions, creating an electromotive force called the streaming or electrofiltration potential. This is influenced by factors like differential pressure and salinity of the solutions. In summary, understanding these processes helps interpreting SP measurements accurately, as they highlight the underlying mechanism that generate the observed SP deflections. What is SP useful for? And what about its applications? Well, SP measurements can be effectively used to estimate the volume of shale, or VSH, in a formation. This is because clay minerals in shale have charge imbalances that restrict the movement of ions, affecting the current generated. Essentially, the presence of these clay minerals alters the SP responses, making it a useful indicator for identifying the shale content in the formation. Another key application of SP measurements is estimating the resistivity of formation water, or RW. This value is crucial for calculating water saturation using the Archie equation. Ideally, formation water resistivity is measured directly from a sample of formation water. However, if it's not possible, the SP responses in a water-bearing formation can be used instead. The SP deflection on the log reflects the resistivity contrast between mud filtrate and formation water. By knowing the resistivity of the mud filtrate from the API mud test at the well site, we can determine the value of RW. SP measurements can also be used for well-to-well correlation, defining formation boundaries and determining formation thickness. However, since SP measurement depends on mainly the fluid characteristics, it might not always be the most reliable method for this task. Next, let's consider how logging conditions affect the effectiveness of SP measurements. Be aware that SP responses are not valid in wells drilled with oil-based mud or air because there's no electricity continuity between the formation and the downhole electrode. Similarly, SP measurements are invalid in casing due to the conductivity of steel. The best results come from water-based drilling fluid with a significant contrast between mud filtrate resistivity and the formation water resistivity. However, SP measurements become less useful when the salinity of the mud filtrate and formation water are similar. For instance, in formations with saline water, drill with saltwater-based mud, or in formations with very fresh water, drill with very fresh water-based mud. Now, let's think about the physics behind SP measurements. Remember that SP tool captures the potential difference between a downhole electrode and a surface reference electrode called fish. Well, since the downhole electrode is in the mud column, the SP deflection observed on the log only shows the potential drop in the borehole, not the full potential drop within the formation. Therefore, the observed SP response reflects only part of the total electromotive force. This means that for accurate measurements, the surface electrode should be isolated from surface potentials. Any excess potential on the surface fish can cause errors in the measurements, which are unpredictable and can be corrected later. Possible sources of excess potential include magnetism from the measuring wheels, line leakage, non-static fish conditions, and welding. Therefore, ensuring a good earth-ground reference for the surface fish is vital to minimize measurements error. In practice, SP tool is never run alone. It usually comes integrated with a resistivity tool, whether it might be induction or a lateral log. With that being said, we will learn now about the SP baseline response in shale. In the image, we can get a sense on how the SP curve is shown in a log. By best practices, the scale of the SP curve is adjusted in a way that the SP baseline is usually near the right side of the track. Be aware that in permeable rocks, any salinity difference between invaded mud filtrate and the original formation water causes a deflection away from the SP shale baseline. By quickly scanning the SP curve, we can distinguish permeable formations from impermeable shales. Additionally, shale also shows a baseline response on resistivity curves. Due to their very low permeability, shales are not usually invaded, and resistivity values at all depth of investigation are equal, causing them to stack, meaning that the curve for the shallow resistivity will read similar to the deep resistivity curve. Additionally, because clay minerals in shale are conductive, the resistivity baseline is typically low, in the range of 1 to 10 ohm meters. The measured voltage of SP tool is dependent on the contrast ratio of resistivity mud filtrate and formation water resistivity, where greater contrast results in larger voltage drop and larger SP curve deflection from its shale baseline. The direction of the SP curve deflection, left or right, is controlled by the polarity of the natural current flow in the formation, which is determined by the absolute relationship between RMF and RW. If the resistivity of the mud filtrate is greater than the formation water resistivity, for example, fresh mud invading salty formation water, current floats into permeable formation and returns through adjacent shales and return back into the borehole. If resistivity of mud filtrate is less than formation water resistivity, as is the case of salty mud invading fresh formation water, the current loop is reversed. That's why we say that negative SP deflection, when the curve deflects to the left of the shale baseline, indicates that mud filtrate is more resistive than formation water. This common SP response is observed in water-based mud, where fresh mud invades formation containing salty water. On the contrary, positive SP deflection, when the curve deflects to the right of the shale baseline, occurs when mud filtrate is less resistive than formation water. This is seen when fresh water causes positive deflection, typically at shallower depth and already behind casing. And when there is no salinity contrast between mud filtrate and formation water, the SP curve shows minimal deflection from the shale baseline. This is a limitation of the SP curve as a permeability indicator. Permeable water-saturated rocks, where the ratio RMF-RW can be mistaken for shale In conclusion, SP tools are valuable in wireline logging because they provide information about subsurface formations. By understanding their origin, applications, and influencing factors, we can make better decisions in oil and gas exploration. Thank you.